I started working with BGP connections, going out to multiple internet service providers and having my router hold the entire internet routing table. This is back in the late 1990s. It contained about 60,000 entries, but now the internet routing table has grown tremendously. In fact, let's go out and take a look at the size of the internet routing table at the time of this recording. It used to be when I started working with BGP and doing multi-homing, and we had about 60,000 routes at that point. Now we're approaching, or we've exceeded 800,000 route entries, and it's probably going to be more than that when you watch this video. And we can do some route aggregation, but sometimes, like if we're doing traffic engineering, we might require that a specific route be injected into BGP. If we're doing multi-homing, that configuration might require that we have the full internet routing table. The bottom line is, we have a problem with scalability with the internet routing table. But there's a protocol that can help us out with that. The protocol is called LISP, L-I-S-P, and that stands for the Location ID Separation Protocol. And by the way, LISP is useful in other environments too, like mobility environments or Internet of Things applications, but it was originally designed to address the internet routing table's scalability issue. Now, as the name suggests, LISP separates a single IP address into two parts: an endpoint identifier, or an EID, and a routing locator, or an RLOC. This would allow, for example, a device to move from one location on the internet to another location and keep its endpoint identifier, or its EID, while updating its routing locator, its RLOC. And when we're trying to locate a specific endpoint identifier, what we can do is ask a map resolver. And a map resolver is going to give us information about the current routing locator for that EID. In this case, let's say that client A wants to talk to client B. Client B is currently at LISP site 2, and client A is at LISP site 1. And that server at LISP site 2, it's got an IP address of 198.51.100.1. Well, that's going to be the address of the routing locator. That's where we need to point traffic to get to client B. And the way the map resolver knows that client B lives at that address is that the router at LISP site 2 registered that information with a map server. And commonly we'll have the map resolver and the map server on the same device, like a router. And RLOCs, routers representing different LISP sites, they register their information with the map server, and then somebody that wants to get to one of those devices, they can request information from the map resolver, and the map resolver is getting the information from the map server. We see that commonly written as MS/MR. For example, let's say that router at LISP site 2 wants to register with its map server. What it's going to do is it's going to have information stored locally. It knows that the network of 192.168.1.0/24 is available at the RLOC router of 198.51.100.1. Well, it's going to send that information up to the map server, and that map server is going to make an entry in its table. So anybody wanting to go to any IP address in that network, we're going to say, yeah, go to this RLOC router. And that map server is going to send a confirmation, by the way, to that registration message. That's going to go back to our RLOC router. And once we know the RLOC that we're sending to, the packet that we want to send to another site, we're going to add on a LISP header, and we're going to add on a UDP header, and that's going to be encapsulated inside of an IP packet with the RLOCs acting as the source and destination IP addresses. Notice that the source in that outer header is 203.0.113.1. That's the address of the RLOC, that router at LISP site 1, and the destination is the RLOC at LISP site 2, 198.51.100.1. And by the way, in that LISP header, it can contain information such as a VRF identifier or a VPN identifier. This is going to give us segmentation and isolation. And in the UDP header, you might want to make a note that the UDP port number that's used by LISP to send data is UDP port 4341. And again, our goal here is for client A to send traffic to client B. Well, the router at LISP site 1 that's going to do the encapsulation of that traffic, it's called the Ingress Tunnel Router, or the ITR. It's going to do the encapsulation. It adds the LISP header. It encapsulates everything in that new IP packet. And when the packet reaches the destination, the router that does the decapsulation, that unwraps everything, is going to be that router, in our case, at LISP Site 2. That's going to be the ETR. At LISP Site 2, that's going to be the ETR, the egress tunnel router. So in this example, Client A wants to communicate with Client B. So the LISP router at LISP Site 1 is going to query the map resolver to say, hey, I want to go to this IP address of 192.168.1.100, and our map resolver says, oh yeah, I've got an entry for that network that contains that IP address. You should go to an RLOC at an IP address of 198.51.100.1. So that's what happens. Client A goes up to its ITR at LISP Site 1, and it's going to send traffic over to the RLOC that it was told to go to by the map resolver that's over at LISP Site 2. It's going to decapsulate that packet and send it on to Client B. Now in this example, we only had one network at LISP Site 2, but we could have had hundreds at that site, all of which were available using that single route locator of 198.51.100.1. This gives us an idea of how LISP can help address that routing scalability issue. We didn't have to contain all those networks that might have been at LISP Site 2. We just needed to know how to get to the routing locator, and we had another table that said, oh yeah, that RLOC will get you to all these networks. And another benefit that we had here, you might have noticed, is we were able to send traffic between private IP addresses that were separated over the internet. And that's a look at some of the benefits and the operation of the Location ID Separation Protocol.